All right, in this video, we're going to talk about what a partial derivative is. At this point, we know derivatives, full derivatives for functions of one variable. Partial derivatives are all about taking derivatives of functions of two or more variables, okay? So this one, I really want to just focus on what it means. We'll do some more examples for more complicated functions, but the purpose of this first problem is to help you understand what all these partial derivatives mean. So let's consider the function f of xy equals 9 minus x squared minus y squared, which graphically is an upside down paraboloid. Paraboloid was one of the graphs we sketched on one of the first videos. This one's turned upside down, raised up 9. And I like to use this one to introduce partial derivatives because it kind of resembles a mountain. And most people are kind of familiar with, walking on the side of a mountain. So imagine you're at the point 1, 2, 4. If you plug in 1 for x and 2 for y, your z value will be 4. So that's right here on the side of the mountain, over 1, over 2, and then up 4. In fact, I drew in the level curve, right, at z equals 4, because you could picture this would be a circular cross-section here. And I drew a trace. Okay, the trace at y equals 2, if you slice through this mountain, all of the points on this mountain that have a y value of 2, you can kind of see an upside down parabola. Okay, so now what we mean by a partial derivative graphically here, imagine you're at this point and you face towards the positive x-axis, so you're facing outward, and then you start moving. Well, if you move in that direction, you're going to start to move down this parabola, right, on the trace. You're going to move down that parabola. What we're interested in is what your slope is. You're definitely going to be going downhill. We can tell that from the graph here, okay? Notice when you move in the x direction along that parabola, your y value is not going to change, okay? Your y coordinate will stay constant. It's going to stay at y equals 2 because you're moving along that cross section. So how do I find the slope? Well, we know slopes are about derivatives. So I would take the derivative of this function. Now the notation here, okay, we're used to df dx or f prime of x. But to indicate a partial derivative, this is a partial symbol. Okay, that's the partial derivative of f with respect to x. So there's this notation, and there's also the subscript notation. F sub x means the partial derivative with respect to x. So we're taking the derivative of our function, treating y as a constant, okay? Literally in this equation, y is equal to 2, literally, right? So if you go back to your equation, you could imagine y being 2 there. You have 9 minus x squared minus 4. It's really just 5 minus x squared. So your derivative is just going to be negative 2x. The 9 and the y squared go away. And if I evaluate that at our point 1, 2, I don't even need the y value. If I evaluate it when x is 1, I get a slope of negative 2. That makes sense. We're going to go downhill. Okay. What if we wanted to move in the y direction? Okay, I'm going to slide this back up here. This is a little bit harder to see. I don't want to really draw in this picture because it's going to be too busy. But can you see if I were to move along in the y direction, face the positive y-axis, I'm going to go down the mountain as well. I'm going to go down this way, right? I'm going to head down here. Now, if I move in the y direction, my x value is going to stay the same, right? However far out I am here, I'm going to stay that far out. So if I want to find my slope in the y direction, I'm going to treat my x coordinate as a constant. Notation-wise, it's the partial of f with respect to y, or f sub y. Again, x would be, the derivative of your x term would be 0 because it's a constant. And I would just end up with negative 2y. Evaluated at the same x and y value is going to give me a slope of negative 4. In first quarter calculus, we saw that there were times too we were interested in the second derivative. And so we can also take second partial derivatives. Notation-wise, that you put the square here so we don't get confused with the first derivative squared. It's the partial square root of f with respect to x squared. Or in the subscript notation, we just denote that as f sub x. What this notation means is you're taking the partial derivative with respect to x of the partial of f with respect to x, what we just found, which was negative 2x. So we're taking the partial derivative of that one more time with respect to x. There isn't a y term anyhow, so the derivative of that would be negative 2. Similarly, with respect to y, it's the partial with respect to y of partial f with respect to y, which is the partial with respect to y of negative 2y, which would be negative 2. And here's what is true too. In first quarter calculus, what did we use the second derivative for? We talked about concavity, right? How the graph was curving. And so quite literally, the way you can interpret these two answers is that at our point, at 1, 2, 4, our graph is concave down in the x and y direction. Go back to your graph and you can see that. Right, at this point in the x direction, right, in this direction, it's concave down. It's an upside down parabola. And again, it's hard to visualize, but you can imagine slicing through this mountain here, you would see an upside down parabola as well, which is concave down. Okay. We also have what we call the mixed partial derivatives. And what the mixed partial derivatives, they're second derivatives as well. We can talk about the second partial derivative with respect to y with respect to x. Let me stick with this notation. So you would work from left to right. That means you're going to take the partial derivative with respect to y of the partial of f with respect to x, which is the partial with respect to y. Remember, that was negative 2x. Remember, when you're doing a partial with respect to y, you're treating x as a constant. So that means this whole thing is a constant. The derivative of a constant is 0. One thing to point out is in the subscript notation, it's backwards, right? It's different. This derivative would have been written as f sub xy, and what you do is you go from left to right. You first find f sub x, and whatever that answer is, you take the derivative of that with respect to y. Okay, so you should probably be comfortable with both notations. Okay, same thing here. Now I want to do the partial derivative of x of the partial of f with respect to y. So that's the partial with respect to x of negative 2y. We're treating y as a constant. This whole thing would be 0. Okay, and again, the notation in the subscript is the opposite order. Okay. What this means, okay, if you're wondering, how, what's the physical interpretation of this? If you are at the point, if I can back this out. If you're at the point 1, 2, 4, let's talk about this one being 0, and you're facing the x direction, so you're facing the positive x-axis. If you were to take a step in the y direction, you can imagine your slope's negative here, right? If you're facing the x direction. What it means is if you were to take a step in the y direction, your slope doesn't change. Your slope is the same. It's the same slope, okay? The fact that that answer is 0. The physical interpretation of the mixed partial derivatives is not super critical. That's not usually a question anybody asks for, but if you're curious, that's what it means. All right. To make partial derivatives a little bit easier, now that you see how they work, when you take a partial derivative, remember that you're always treating one variable as a constant. And let's revisit what happens to constants when from single variable calculus, okay? If you've got a function like sine of x plus 3 and you take the derivative, of course it's just cosine of x and the derivative of 3 would be 0. If your constant's by itself, it's just going to go away, right, when you take the derivative. But when your constant is multiplied by your function, we know the derivative of 3 sine of x is 3 cosine of x. So what's the difference here? The constant doesn't go away. When the constant's multiplied by your function, it stays, right? It just stays there and you take the derivative of your function. When we take partial derivatives in 17C, it's going to be one of these two situations every single time. Either the constant's by itself or it's multiplied by your function. So let me show you. Let's say our function is x to the fourth plus y cubed plus x squared y to the fifth. To take the partial with respect to x, where y is constant, x is my variable, so the derivative of x to the fourth is 4x cubed. Notice my y term here is a constant all by itself. So that's just going to be a number, and of course the derivative would be 0. But on this term, y is constant, but it's being multiplied by my function. So what happens? Your constant just comes down, it stays, and you take the derivative of x squared. Okay, let's try it with respect to y. Now x is a constant. This term's all by itself. It's a constant, it's x, so it's going to go away to 0. Derivative of y cubed is 3y squared. And now the x squared is a constant times my variable, so that just comes down, stays there, and I take the derivative of 5y to the fourth. These would be multiplied together. Okay. Let's do our next derivatives. I should leave that up there, yeah. So the second partial with respect to x, which is just the partial with respect to x of the first partial with respect to x. So we're going to take the derivative of this answer again with respect to x. So 4x cubed would be 12x squared. We're treating y as a constant still, so the y to the fifth comes down, and the derivative of 2x is 2. Let's just go ahead and do this one as well, because this is your mixed partial, where I want to take the partial derivative with respect to y now of the partial of f with respect to x. So now I know I'm treating x as a constant. So the derivative of 4x cubed goes away. It's not there. And the 2x is just going to come down. And the derivative of y to the fifth is 5y to the fourth. And that gives me 10xy to the fourth. Okay, you can come back here now and do your second partial with respect to y. That's again referring to the first partial with respect to y, doing it one more time. 6y, x squared is constant, but it's times my variable, so that comes down. And the derivative of 5y to the fourth is 20y cubed. And then finally, my other mixed partial, which is taking the partial with respect to x of your partial with respect to y. So now I'm treating y as a constant. That goes away, it's by itself. 5y to the fourth stays there, and then the derivative of x squared is 2x. So notice your 2 second partials here always refer back to your first partial derivative. Same thing with the x ones. Right? And another thing to notice is that your mixed partial derivatives end up being the same. And that's not just a coincidence. Under most circumstances, this is always going to be true. Your mixed partial derivatives will be the same. So that's a nice way to check, right? Make sure you get the same answer for both of those. Let's do another one. All right. And probably a good idea is to maybe pause the video, and see if you can work on finding all 6 partial derivatives, your first and all 4 of your second partial derivatives for x over x plus y. Okay, and then when you tried it, come back and look at this. With respect to x, y is constant, but because I have an x in the top and the bottom, I'm going to need to use the quotient rule. And the way I remember the quotient rule, it's the bottom times the derivative of the high, the top, minus the top, the high, times the derivative of the low. and then over the low squared, right? And when I simplify that, I get y over x plus y squared. Let's do them all with respect to x first, or at least the first. Let's do the first two. How about that? Because now if I was doing f sub x, I'm still treating y as a constant, but there's a nice difference here. If y is a constant, go back to think about single variable calculus. If you have a constant in the numerator and you're going to ask to take the derivative, rather than use the quotient rule, it's much easier to bring up the denominator and just use a chain rule, right? If y is a constant. So that's what I'm doing here. I'm bringing this up, and then I'm taking the derivative with respect to y. By the chain rule, it's negative 2y stuff to the negative 3 times the derivative of the inside. With respect to x, the derivative of x would be 1. With respect to x, the derivative of y would be 0. So that gives me negative 2y over x plus y cubed. Let's do f sub y and f sub yy before we do the mixed partials. Okay, so same idea as the one I just did here. If I'm taking the partial with respect to y, x is a constant. So my numerator is a constant here. So rather than using the quotient rule, I'm going to bring the denominator up and do a chain rule. The derivative of x times stuff to the negative 1, bring that down, negative x stuff to the negative 2. The derivative of the inside will be 0 and then 1. And fortunately, f sub y, if I take the second derivative with respect to y, holding x as a constant, this is also still a constant. So I can do the same trick. I don't need to bother with the quotient rule. Bring that up, do another chain rule, and you should end up with 2x over x plus y cubed. All right, let's talk about f sub xy. I might have to back this out, yeah. At least for the beginning. Remember, f sub xy, you're going to look at f sub x, because we already took that derivative, and now take the partial with respect to y of this answer, which means we're treating x as a constant. If x is a constant, y is my variable. Unfortunately, I have a y here and here, so I can't get away with it. I'm going to use the quotient rule. Low d high minus high d low over low squared. And if you simplify that, I factored out an x plus y, and I got it down to being x minus y over x plus y cubed. Now, if you trust yourself, remember that the two mixed partial derivatives come out to be the same. So if you trust that you did this one right, you don't need to do any work. This has to be the same. Of course, you know, would it be a good idea to do this one and make sure you get the same answer? Of course, right? The theorem, by the way, that tells you that again, under most circumstances, that these two will be the same is called Clairaut's theorem. F sub xy will equal f sub yx. I haven't seen one yet in 17C where they don't equal each other. So, okay. These partial derivatives, we've been doing them for functions of two variables, but I think it's important to recognize that we can do partial derivatives for functions of as many variables as we want. If I've got a function of x, y, and z, then, and someone says they want to know the partial derivative with respect to x, well, what would make sense? We're going to treat not only y, but also z as a constant. Because y and z are constants, and the whole sign of this is the whole thing's a constant, right? It's being multiplied by my variable, so it just comes down for the ride, and you take the derivative of x squared. There's f sub x. For f sub y, now x and z are constant. So the x squared's constant, the z's constant. So how do we take the derivative when you have a constant times the sign? The constant just comes down. The derivative of sine of stuff is cosine of stuff. The partial derivative of the inside with respect to y would be 2 here and 0 there. And then finally, with respect to z, we would treat x and y constant. So once again, the x squared comes down. The derivative of sine of stuff is cosine of stuff. This time, the y goes away, and the derivative of 3z is 3. Sometimes your equation will be all mixed together, your x, y's, and z's. And so you may remember from first quarter calculus, this is implicit differentiation. So, and the way we're going to do this is we want to find the partial of z with respect to x. So we're going to be treating y as a constant, and we're going to assume that z implicitly is a function of x. That's, if you go back to 17a, when we did dy dx, we assumed y implicitly was a function of x. So it's kind of the same idea. Okay, so we're taking the derivative of both sides with respect to x. Derivative of 2x would be 0. Y is being treated as a constant. Z is a function of x, so the derivative of z squared is 2z times the derivative of z with respect to x. For the right side, okay, x is our variable, right? We want it with respect to x. Y is constant, but we're assuming z is a function of x as well. Because the x and the z term are being multiplied together, we're going to need the product rule. One way to do it is you could pull the 3 and the y out and just deal with the x and z separately. I decided to just let 3x be f, yz be g, and use the product rule. The derivative of the first with respect to x is 3 times the second plus the first, and the derivative of yz, y is a constant, comes down, times the partial of z with respect to x. From then on out, it's just algebra. You've done this before. You want to get the two terms that have your partial of z with respect to x on the same side. So I subtracted the 3xy term and moved the 2x over to the other side. Factor out your partial of z with respect to x, and then finally divide to get the partial of z with respect to x by itself. And so I would recommend try to find the partial of z with respect to y for extra practice. On the next video, I'm going to show you now how these partial derivatives show up in some biological examples.